All right, last time we started section 6.1 and we were taking a look at uses of rational numbers. And we're going to move on to some models or visual representations of rational numbers today. So there are 4 examples, and I'd just like you to jot down quickly what fraction of each example is shaded in. And then we're going to chat with one another and make sure that you have the right perspective from these particular diagrams. It looks like we're done or close to done. What did you write for A? What do you think? It is 1/6. If a student did this wrong, what would you expect their answer might say? Might say 1/4. So why might it say 1/4? Yeah, if you're just counting the boxes, there's 4 boxes, and one of the 4 of them shaded in. That's a reasonable place to go. And on this one, what you can do to make it visually easier to see is to make the boxes all the same size by just changing the bottom box to having, 3 pieces instead of 1 piece, and you have what you were telling me, which is 1/6. B has kind of the same problem, right? In the sense that there's 1 box out of 5 shaded in. It's a little bit easier to see that confusion could be made in this regard because the boxes are closer in size. And it's also trickier on this one to see, maybe, depending on your perspective, how to make the boxes equal. So instead of just adding in additional lines, the easiest option is to actually remove some lines as well. So if we remove these 2 lines, then it makes it look just like one long strip. And then we can add in the line like we did on the last one so that we have 4 boxes. So we end up with 1/4 on this one when we equalize the size of the boxes. How about C? 2/7. Any idea what might be a common misconception on this one? So this one looks a lot like the way we would cut like a pizza, which are typically cut straight across and they're in 8 slices. So if you're just looking at this as a cursory glance, it'd be really easy to say that this is actually 2/8 instead of 2/7 because of a reference point that you have, like a contextual reference point that's not actually the image you're looking at. So something to be aware of. How about part D? 7/12. Now, the reason I put this one in here is because it's actually a very stark contrast to the last 3. The first 3 that are shown are whole diagrams where part of them are shaded in. But the last diagram is all these individual objects. So it's more like a ratio comparison, like we talked about last time, instead of like a portion of a whole. Like 1/4 of my income is the whole, my income is the whole, 1/4 of it is a portion. That's kind of the first 3 diagrams, but the last one is a ratio, kind of a comparison. So lots of different sort of visual representations, and there will be another one that we see here in a moment too. A little bit of historical context for fractions, rational numbers. The Egyptians actually started the process of using fractions, and they used fractions that always had a numerator of 1. Now that's nice when you're talking about something that's already in our world having a numerator of 1, but not all numbers are written that way. Like the 7/12, I think that was the last picture we just did, right? 7/12. What do? I mean, it's not 1 over anything. Well, they broke it apart into pieces that were the equivalent. And so they would write 7/12 equivalently as 1/4 plus 1/3. So that feels a little bit awkward, right? Because it's not what we're familiar with, but that's how they did it when it was the Egyptians. The Greeks adopted fractions, and they used denominators of 60 from the Babylonians. It's still presently used in the measurement of angles. So when we're measuring angles, we use measurements of 60 or 180, those kinds of things quite a bit. And then whenever you see Hindu or Hindu Arabic, that's talking about our number system. I remember seeing something, a while back, like, I just can't believe it. My child is learning Hindu Arabic numeration system in school. Well, that means they're learning our system, right? So it's those words that just kind of sound different to our ears. This is our numeration system. The Hindus specifically developed our modern bar between the numerator and denominator, and that happened in about the 1500s in Europe. So it's really not been around all that long. All right, so the next thing we're going to look at are actually the three different models for fractions or rational numbers that we're going to be using. The first one we've seen quite a bit. In fact, the examples over here, the first three examples are this example. It's an area model. Usually we use a rectangle. It says use a rectangle. Technically, you could use any shape, but rectangles are the most maybe convenient to use. So using a rectangle to do an area model would look something like this. So we're going to do an example of 3/4 on all of these. And the first one we're going to do is the rectangle model. So it's going to look much like the rectangles that we saw in the first example of our day. And we would draw, that's really thick, let's make it thinner. We draw a rectangle, and then we would split it up into the number of pieces in the denominator. In this case, that's a 4. So we would split up into 4 pieces. And the numerator tells me how many I shade in. It says 3, so here's 1, 2, 3. So this is one representation of the number 3/4, an area model. You could equivalently draw 3/4 of a pizza, like a circle, right? Or other shapes too, but this one works pretty well. The second one is a number line model. We haven't seen this one used yet. A number line model works very nicely as well. So instead of drawing, a rectangle, we're going to just draw the number line. And it has to start at 0 and it has to end at 1 for what we're doing. And then again, because the denominator is 4, we're going to split the box or the line between 0 and 1 into 4 equal pieces. 4 is really nice because you can split it in half and then you can split it in half again. So visually it's easier to do. If you were working with something that's harder to split, sometimes it's easier not to put the 1 and the 0 on there to begin with, but just to put the 0 and then do however many hash marks you need to get to 1, just to keep it in perspective. And then 3/4 would be 3/4 of the way. It would be right here on our box, or on our line. And the last model is called a set model. We've seen this one used. That was the 7/12 diagram that you had over here with, there we go, with the blue circles shaded in and then the vacant looking ones. That's a chips model or a set model. And goodness, I keep flipping to my slides too fast. And so the easiest way when we're given 3/4 and told to draw the model is to draw the objects that are in the denominator, that many of them. So in this case, it would be 4 objects. So we would draw, 1, 2, 3, and 4. So we would draw 4 of them. And then we would shade 3 of them in, because that's the numerator, to represent 3/4. This is fairly limited, though. Like, let's say, for example, you had 5 quarters, and you were told you wanted to take 3/4 of the 5 quarters. Well, 3/4 of 5 quarters is not an easy picture to make amends to. It just doesn't make sense, right? 3/4 of 4 quarters, sure, you take 3 of the 4 quarters. But when it's not, determined in advance how many coins you have, or when it is determined in advance how many coins you have, and it's not the value that's in the denominator, it's not real easy to work with. So this has some limited usability. Fundamental law of fractions is something that you are familiar with, maybe not written in this form. And it says the following: if we have a fraction a over b, and n is any non-zero integer, then if you multiply a by n and b by n, the value of the fraction doesn't change. In particular, we use this with addition and subtraction in order to get common denominators. That's this where we see this used. It can also be used when you're kind of trying to compare things, right? If I have, 3/4 of a cookie and you have 2/3 of a cookie, and we can't see them, right? And we're just looking at the numerical values, we can compare them by getting common denominators as well. So as long as we multiply the numerator and denominator by the same value, it doesn't change. Simplest form uses that idea instead of multiplying the numerator and denominator by the same value, and it divides it. So it's the idea of simplifying values by dividing. So you're dividing the numerator and the denominator by the same thing. So maybe you're dividing them by 2, or maybe you're dividing them by 7, whatever they have in common, in order to reduce them so that they do not have any common factors besides besides 1. Okay? So we're going to do an example where we write some equal values to one we already have. So our value that we're starting with is 7 over negative 14. And there's lots of ways that we can write equivalent fractional values to this. So I'd like you to jot down 3 that come to your mind, and then we'll kind of talk together about what you wrote, and I'll add some to it that maybe you didn't think about as being also equivalent. Okay, so remember, you're allowed to multiply top and bottom, you're allowed to divide top and bottom to create an equivalent fraction. Those are your operations. Can somebody tell me one of your equivalent fractions to 7 over negative 14? Negative 1/2. So what did you do to get negative 1/2? Yeah, you divided by, nope, 7. Yeah, you divided by 7. You divided the top by 7 and the bottom by 7. And to be honest, you actually divided by negative 7 because you switched where the negative was as well. So interestingly enough, though it seems sort of silly, an equivalent fraction to the one we were given is actually this one too, right? That's actually multiplying or dividing the top or the bottom by negative 1. So we'll throw that one in there. What else did you get? Somebody tell me one.
14 over negative 28.
Okay, say that louder. 14 over
Negative 28.
negative 28. So what did you do, Mackenzie?
Multiply by 2.
Yeah, multiplied the top and the bottom by 2, right? Okay. What else? Give me one more. I saw you guys all writing. I'll have stuff written down.
Negative 21 over 42.
All right, negative 21 over 42. So that's bigger numbers. So what did you multiply by?
Negative 3.
Negative 3. So if you multiply by negative 3 on the top and the bottom. Okay, so Cora, right? Okay, so Cora told me the negative 1/2 at the very beginning. And it's interesting to think about that one because if you actually have negative 1/2, it might be easier to use the negative 1/2 then to generate more equal fractions. For example, if I have negative 1/2, I also have negative 3/6, right? So it doesn't have to be generated from the original first one you start with. It'll still be equal if you generate it from one of the ones you've sort of landed on in the middle of there too. So you have lots and lots of options. We can do negative 10 over 20, that kind of stuff. All right, any questions on that? Okay, so now we're going to look at finding the simplest form with a little bit of a twist. This one says 42 squared over 35 squared. Okay? A little bit large. You really are not trying to multiply 42 times 42 and 35 times 35. That's not what we want to do. Okay, so let me just tell you that right now. That's not the goal. But one of the reasons I bring this one up specifically is because a very common misconception when we start thinking about canceling things from numerator and denominator is this sort of unintentional, I can cancel anything. So you can't cancel anything, right? So when we look at this simplest form description over here and it talks about it, what we can do is multiply or divide, nothing else, right? So if there had been addition or subtraction on the top and the bottom that mirrored one another, you couldn't reduce it. And likewise on this one, because there's squareds involved, I can't just eliminate the squareds. They don't go away like that. Does that make sense for everybody? Okay, so when I'm looking at the 42 squared, I told you we're not going to actually do 42 times 42, but we are going to write it out. It means 42 times 42 and 35 times 35. And because it's all multiplication on top and because it's all multiplication on bottom, I can look at things that 42 and 35 have in common and reduce it from there. What are 42 and 35 both divisible by? 7. So what is 42 divided by 7? 6. And what is 35 divided by 7? 5. So that's the first 42 and 35. But if I can do it with one pair of them, I should be able to do the exact same thing with the other pair. So now I can reduce this one and make it 6. And this one and make it 5. Does that make sense to everyone? Okay, so at this point, 6 and 5 don't break down in any way that they simplify. I mean, I know 6 breaks down into 2 times 3, but the 2 and the 3 still don't simplify with the 5. So there's no other reducing that can be done. So at the point when there's no other reducing that can be done, we're just going to multiply the terms that are on the top. So in this case, I get a 36. And I multiply the terms that are on the bottom, and I get a 25. And that's my simplest form for the fraction I began with. All good? Okay. The next thing we're going to look at is basically comparison of fractions, how we decide if one fraction is equal to another one or larger or smaller than another one. So our first definition of this actually talks about equality. So if I have two fractions, a over b and c over d, they are equal if and only if AD is equal to BC. And you'll notice that AD is this diagonal and B and C is on this diagonal. So you multiply the two diagonals together, they should equal to the other multiplication of the diagonals if the fractions are the same. Now this isn't the only way to determine if fractions are equal, and in fact it might not even be a great way to do so, depending on the fractions that you're working with. So we're going to do an example that's actually deciding if fractions are equal, and we're going to actually compare them, in this description sort of phrase, 4 different ways. I'm going to show you 4 different ways to decide if they're equal. And I don't care which one you use later on. So you can pick whichever one you like. Sometimes you might actually choose one and then not choose it the next time based on the fractions that you're given. So I want you to be aware of it. One of the things that you will see, especially if you haven't taken any of the elementary ed math courses here at OBU, is that this textbook and Dr. Marsh and I do a lot of giving you lots of ways to do something. And the reason that we do that is because just because your textbook and what you're teaching in your classroom may be fine and good and correct and all of that stuff, doesn't necessarily mean every child's going to resonate with it and take it up and really just be able to do that very well. And so having a tool belt of other options is really helpful so that you can say, okay, that did not work well for this kid. What other way can I show them to explain this? And it just might be the one that makes sense to them, and then they're able to do it. So that's what we're looking for here. So the first way that the first problem we're going to do with this kind of an idea is we have 3 over negative 12 and negative 36 over 144. Let me first say something about this negative. Just put it somewhere. Okay, so put it on the top, put it on the bottom, it doesn't really matter. And to be perfectly honest, the numbers are both negative, right? So I can ignore them. I know that they're the same sign, right? They're both negatives. What I really am trying to figure out is if 3 over 12 and 36 over 1 over 44 are the same. Does that make sense? So for the meantime, we're just going to ignore the negatives because we know they sort of match up already. All right, so the first way that we're going to check to see if these are equal is with the theorem we just talked about, because we just talked about it. So this is theorem 6.2's, strategy. And what it says is that if I have the fraction 3 over 12 and the fraction 36 over 144, and I want to know if they're equal, I'm just going to put an equals with a question mark in between. I don't know really for sure that they are, right? It's me asking the question. What has to be true is that if I multiply the diagonals together like that, I get the same thing. So I want to be able to multiply 3 times 144 and multiply 12 times 36 and compare them. So grab a calculator out if you don't have one. I will do the same. What is 3 times 144? 432. What is 12 times 36? It is 432 as well. And those, in fact, are equal. Therefore, the fractions are equal, right? This proves that the fractions are equal fractions. Okay, does that make sense? It's a pretty straightforward process. However, if the numbers got large enough and were awkward enough, and or you didn't have a calculator at your ready hand to just double check it real quick kind of thing, this might not be your best strategy, right? It just might not. So this is one option. We're going to do option number 2. And option number 2, we're going to simplify and compare. So what do I mean? Well, we have two fractions. We have 3 over 12, and we have 36 over 144. And we're just going to keep simplifying them down until they're in their simplest form and see what we end up with. Now, we know what we're going to end up with. They're going to be the same. We know they're going to be the same because we already did the problem a different way. All right, so that's the expectation moving forward. 3 and 12. What do 3 and 12 both divide by? 3. So if I divide the top and the bottom by 3, 3 divided by 3, of course, is 1. What's 12 divided by 3? 4. All right. You may not, looking at 36, know what the biggest number is that divides them, but you should be able to look at it and know something divides them because they're both even at the very least, right? So your bare minimum that you can look at this and say, I absolutely know beyond a shadow of a doubt is I can divide it both by 2. Agreed? You might look at this and know that you can both divide them both by 12 because it's the 12 tables, right? Multiplication tables that are pretty commonly taught. So I'm going to start with division by 12 with that premise, and if that didn't resonate with you and you want to divide by 2 first, then do that first. Doesn't matter. If we do it with 12, what is 36 divided by 12? 3. And 144 divided by 12 is 12. And to be perfectly honest, it matches the 312 we had right there before. That typically doesn't happen in the middle of this, so I'm going to go one step further just to show that they both reduce to the same thing, which of course they will. And I have my 1/4. So again, this is telling us that we have equal fractions. Okay, so far so good? All right, the next two methods are similar to one another. Number 3, we're going to find a common denominator. And number 4, just so you know where we're headed, is that we're going to find the least common denominator. What do I mean to find a common denominator? Well, finding a common denominator just means using the two denominators you have and multiplying them by one another. So we have the value 3 over 12, and we have the value 36 over 144. And 12 will be multiplied by 144, but if you do it to the top, the denominator, you have to do it to the numerator. And then the 144 will be multiplied by 12, therefore 36 will as well. We've already done 3 times 144. We found that out. That was 432. What is 12 times 144? Yes. Same thing on the second one. We've already done the top. It's 432. We've already done the bottom now as well, right, from the previous step. And it's 1728. And in fact, they're the same again, right? So again, this tells us that we have equal fractions. Okay, so the reality is that that's definitely overkill because 12 and 144, the denominators that we have, are very related to begin with. However, sometimes you look at fractions denominators and you're just not sure what they have in common. to make them equal. It's just not quite that straightforward, and so this is a good method for just plowing through, even though the numbers get big, without having to do a lot of like breaking things down to decide. If you do happen to notice, and this is a really good example of one where you might, that the denominators of the two fractions have something that makes them, in common. You can get a common denominator, any common denominator, but in this case, the least common denominator, by recognizing what the earliest multiple is that they have in common. And in particular, on this one, if I multiply 12 times 12, I get 144, which is the other denominator. And so this might be the easiest method on this particular problem, to be perfectly honest, because 3 times 12 is 36, and the denominator gives me that 144, and I'm done. Is that always going to be the easiest? Actually, least common denominator is often not the easiest. It's often the most challenging because you're trying to break things down to figure out what that least common denominator is. But on this one, it ends up being very nice. And so again, this tells us that our fractions are equal. All right, so let's say instead of getting equal fractions like we did on these, we found out that they were not equal. Okay, that's fine, they're not equal, but another sort of question you can ask then is, well, which one's bigger? And that's what our next theorem is actually talking about. It's comparing them in the terms of what happens when one is bigger. So again, if you have that a, b, c, and d, and you have that fraction a over b and c over d, then it's actually true that a over b is greater than c over d if the ad multiplied is greater than b and c multiplied. And what you see happening again is the cross multiplication, checking that, right? And seeing what happens when we multiply across those diagonals. It does matter that you start from the top down and not from the bottom up to make your comparison. So you have to remember that the order of this matters. We start in the top left-hand corner, but if you think about it, that's probably what you do anyway, because that's how we read, is from top down and left to right. So it works just like that. All right, so let's take a look at example 5. Oh, let me tell you one other kind of maybe limitation of this. This only tells you comparing two fractions, which one's bigger and which one's smaller. It doesn't tell you what happens when you have 3. So when we move into this example over here, it's not super friendly to use the fact that we just learned, because I'd have to take 2 of them at a time and figure out which one's smaller than the other one. And then I'd have to take one of those with the one I didn't do and figure out which one's smaller, right? I mean, I'd have to do that process multiple times to figure out the order. So there are other options for number 5 that are simply easier to work with. We've talked back over here about comparing fractions in terms of equality. It's the same options when we're comparing them, and we know that they're not equal. So these fractions are, in fact, not equal, but they do have an ordering to them. So when you're taking a look at those particular denominators, what do you notice about them? They're all multiples of 5, right? So it tends to mean that getting a common denominator, in fact, a least common denominator, wouldn't be too hard to do, because they're all very friendly multiples of 5. So I'll take them in order. We'll do 13 over 20. We have 3 over 5. And we have 7 over 10. And I would like to multiply the 5 by something to get the common denominator. What would the common denominator between these denominators be? 20 would work, right? So what would I multiply 5 by to get 20? 4. So I would do it on top and bottom, like so. How about 7 and 10, or the 10 specifically? Yeah, I would times by 2 to get the 20, and then I would therefore do the 7 as well. So the 3 over 5 becomes what over 20? 12 over 20. And the 7 over 10 becomes 14 over 20. This one says ascending order. Ascending means smallest to largest, right? So which of these 3 is the smallest? Yeah, this is the smallest. I'm just going to label it with the number 1. What's next? 13. And last? 14. And, oops, I don't know why I said 4. How about 3? We're going to write them in order, but we want to write them in order using the original notations, not the 12 over the 20 and the 14 over the 20. So we're going to start with, instead of writing 12 over 20, we'll start with 3/5. You can put a comma if you'd like. I'm actually going to use less than symbols to remind myself that I'm going in ascending order. The second one was the 13 over 20. And the last one is the 7 over 10. Any questions? Okay, so this one does compare just two fractions. So you could totally use theorem 6.2 that we had seen, or 6.3 that we had seen before, where we cross multiply to see which one's bigger on this one. So that's going to be the first method that we use. We're trying to decide which fraction is bigger, or if they're equal. So I am going to do method number 1, our first option, and we're going to see 21 over 230 and 51 over 215. And we're going to cross multiply.
430.
Oh, sorry. Thank you. 430. The 215 was right, wasn't it? I just had the first one wrong. Okay. All right. Thanks. All right. So we're going to do the cross multiplication. So again, we have to start with the top left corner. So it's 21 times 215. And the other one is 430 times 51. Okay, what is 21 times 215?
4,550.
Lovely. And how about 430 times 51? Very good. 930. There we go. Thanks. It's a terrible looking 9. Let's try again. All right. Which one's bigger? It's 21,000, right? It's bigger here. So what that means is I can go back up here and put it right there. Right? It's a direction that the inequality is the same. So the symbol that should go in the blank is actually that symbol. But once again, let me show you a couple other ways to do it. So we talked before about one of these, and then another one of these I'm going to show you is new. So one option, or option number 2, is to reduce. And reduce, simplify, whatever words you want. That's not even the word I want. How about we call it common denominator? We'll kind of group them all together. The goal is to get them to look alike. All right, so we have 21 over 430. And if you take a look at 51 over 215, and you simply look at their denominators, what do you notice? 430 and 215. Okay, what about 5? They are both multiples of 5. There's something that's easier to work with. Sorry, what did you say? Maybe.
215.
What about 215?
Because it goes down to 430, you just add it.
Yeah. Okay, so they both actually divide by 215. And instead of actually using it in that fashion that you described, and also in the words that I used by calling it reduce, it might actually be easier to multiply this one by 2 to get them to match, simply because the numerator is 51, which is obviously not divisible by 215. And I'd have to break it down differently or increase it differently, right? So it's just kind of messier. So I have the 21 over the 430 on the left, and this is 430 on the right. And what would the numerator become? Yeah, 102. And clearly, that's the bigger one, right? Because it's got the bigger numerator when the denominators match. So the original fraction would look like that, just like before. Here's the new one. Because of the way that the question is worded, it doesn't tell you how you have to do the problem, right? It just says to decide. So any way that you decide, and I don't mean just, I shouldn't say any way, but any way within the realm of fractions that you decide would be appropriate. What is not appropriate for you to do is for you to put them in your calculator and compare the decimals. Okay, so as far as we're concerned right now, decimals is in chapter 7 and we aren't there yet. Okay, so we're not doing anything with decimals right now. So the third option that we're actually going to look at is actually estimation. So estimate slash, I'm going to slash reasoning through it. So take a look at these fractions. The first fraction, 21 over 430, compared to the second fraction, 51 over 215. Compare numerators. Which numerator is smaller? The first one, right? It's got a 21 in it. It's smaller. So this one has a smaller numerator. Now, if the denominators matched and you had a smaller numerator, it'd be the smaller fraction. The denominators don't match, but it's something to be aware of, right? That's what I was deciding in the middle one there, right? The numerator was smaller. The fraction's denominators matched at the ending of the problem. So therefore, I made a decision. But that's not the only thing you can compare. You compare the denominators as well. So if I compare the denominators, the first one has also a larger denominator. Now, a smaller numerator means the fraction would be smaller if the denominators were the same. But what does a larger denominator actually mean? It means smaller as well. I was trying to explain this to one of my children yesterday, right? If I have 7 cookies and I divide it among 15 people, we get fewer cookies than if I divide it among 5, right? So if you've got a bigger denominator, everything breaks apart into smaller amounts. So both of these things make the first fraction smaller. So that's sort of reasoning it out. Another thing you can do in terms of this that kind of falls in this category is estimations, because estimation is not precise, it's not exact. But if you take a look at these values, right, 20 over 40 would be really close to 21, why does that say 43? 430, get my zero in there. 21 over 430 would be really close to 20 over 400, right? It would. So if we thought about sort of looking at 20 over 400 instead, and then we were able to divide by 10 on top and bottom, leaving you with 2 out of 40, and divide by 2 to leaving you with 1 out of 20, right? This would be pretty close to the value I started with, 1 out of 20. I should probably put approximation anyway. It'd be close. And if you looked at the second one, 51 over 215, it'd be awfully close to 50 over 200. Well, 50 over 200 is 1/4. So clearly 1/20th is smaller than 1/4. So you can also think of it from an estimation reasoning standpoint. So there's lots of ways to do the problem. But what you can't do is just put the symbol in and not tell me why you think that. So I don't necessarily care what you use for your justification as long as we're in the realm of fractions, but you do have to justify it. So pick a method, use that method, justify why you chose that symbol between them. Sound good? Okay. Rational numbers have a property called denseness. Doesn't mean they're like dumb. Okay, denseness, the denseness property for rational numbers says the following. Given 2 rational numbers, a over b and c over d, there will always be another number in between them. And the easiest way to sort of picture this is from a number line, right? Any 2 numbers that are not the same number on the number line have space between them, always. And that's what this is saying from a mathematical descriptive point of view instead of a visual graphical perspective. One of the ways to find a number halfway between something is to add the 2 values together and divide by 2. That's how we find the midpoint. If you had 2 test scores and you wanted to find the average, that's what you would do, right? If you wanted to figure out what your average monthly salary is, you'd add all the months together and you'd divide by the number of months. So that's one way to do that, to find a value in between them. But that's not always the easiest way to do so. There's actually a really very friendly one here. It's in Theorem 6.5. What it tells us is that we have 2 rational numbers, a over b and c over d, that if we add the numerators together and we add the denominators together, the fraction will be between the 2 numbers we started with. And that's really easy. Because adding two fractions together and dividing by 2 is always going to be more complicated than adding two whole numbers together and adding two whole numbers together, which is what this theorem is telling us we're able to do. And the example that we're given is exactly one of those cases where I would not want to add those fractions together and divide by 2. That would be horrendous. Those are terrible looking fractions. But property 6.5 that we just did, or theorem 6.5, tells us we don't have to. It says we can add the two numerators together, so 35 and 7, and add the two denominators together for 27 and 92. So I have 40 on top. What's my denominator? 519. This value is, in fact, in between 33 over 427 and 7 over 92. And if you're sort of skeptical and you're like, oh, I don't know about that, you're welcome to use your calculator, put them all back into decimal form, like into a decimal form, for you to visually verify and say, like, oh, yep, that's true, it is. And that's fine, nothing wrong with that. It's not how you're going to justify anything for me, but it is something that you can confirm for yourself. And so then why must there be a number between these two fractions? We found one. Why does it have to exist? We just talked about it. Why does it have to exist? Yep, there's space if you think from a graphical perspective, right? So if you want to write this description here from a graphical perspective, you can say much like Mackenzie said, as long as the two numbers aren't equal, there's always space in between them. Hence, that space represents another number. If you want to write it from the definitional perspective or the theorem perspective from 6.4, you can do that as well. I'm going to write that one down just because that's the one I have in my notes. They're both fine. But it's all about the fact that they're not the same and rational numbers are dense. So because the rational numbers are dense, that is, you can always find a point. I'm going to say halfway, and then I'm going to be more vague and say partway. It doesn't really have to be in half, but it's easy for us to imagine cutting something in half. So partway is more accurate because it doesn't have to be exactly in half, but partway between two numbers. Okay. We're going to do one more example. This is usually where I end up on the first week of class with 2 days, so I'm not concerned that we're not going to finish. And it's actually really good because the Success Center is not open until Tuesday either.
Is there a math person this semester?
There are 2 math people this semester, and we'll talk about that in a second. So let's do one more example, and then we'll talk about homework and shifting dates, okay? I'm going to pause for today. All right, a student simplified the fraction m plus n over p plus n to m over p. So this is a very typical kind of question that would occur in that connections section, part C section in your book. So the first question I'm going to ask, because I'm going to break them down here, is what do you think the student did? Yeah, they canceled out the n's. They eliminated the n's in some fashion, you bet. So they canceled out the plus n over the plus n. And actually, it's not that uncommon. It wasn't that much long ago, a few years back, and I had a student in this course on a final exam You know how we just canceled the zeros a minute ago when it was 20 over 400? She canceled 9s on top and bottom, just straight across. Just canceled a whole bunch of 9s. You can't just cancel numbers, right? But we do it with zeros, so it kind of feels like you can just cancel numbers. Well, this is a very common misconception for students. If I can cancel something, why can't I just cancel the addition? That's what the student did. Why might they believe this is a valid operation? Well, because we do it with multiplication, right? So it works with multiplication. Right, like in simplifying fractions and so forth, right? Like if I had m times n over p times n, I would in fact be able to cancel them to give me m over p. That's why they think it's okay. So one of the things that in math circles people talk about a lot of times too is using that phrase canceling is so bad because we mean so many things by it. We mean adding things to 0 and that cancels. We mean dividing or multiplying by 1. We mean lots of things with the word cancels, and so people don't like the word cancels sometimes for that reason. But anytime we have an operation that does something, there is a tendency to want it to work that way for other operations. How would you help the student? How could you help them to know this doesn't work? Beyond just saying it works for multiplication. Yeah. Plugging in numbers, examples is a really good way of doing that. So a numerical example. Extraordinarily helpful. So we're going to do a numerical example as making the numbers like this. So we just need a number added at the same value added to the end. What is 2 plus 3? And 5 plus 3? 8. Okay, so the 5 over 8 is actually the answer if we did this. If the student were allowed to cancel like this, what would they get? Yeah, they would get 2 over 5. And these are not the same. 5 over 8 does not equal 2 over 5. And if you wanted to make sure for reals that it didn't, there's lots of things you could do, right? You can do common denominators. You can look at the reduced fractions. All the things that we did before. They're not equal. And therefore, the original idea of canceling the plus 3s or the plus n's in general doesn't work. All right, so what's going to happen, I'm going to leave the recording going for fall of 2022, is we will push the assignment to be finished next time. So we will finish 6.1 next time, and we will start and hopefully get really far into or finishing 6.2. Next time we will also do group work for 6.1 in class. So this assignment will not be due until Wednesday. The Success Center, we do have 2 tutors in the Success Center this semester. We have Jenna and we have Destiny. So you might know them from some of your other classes. They've both taken all of our elementary math ed classes, and so they're going to be fabulous.